Welcome to What's a P-Value? If you read a few scientific journal articles, it's likely that you'll come across the term p-value. For example, you may read that the p-value of some result is 0.004. Or you might hear someone say that a result wasn't interesting because it had a p-value of greater than 0.05. Here we'll talk about what a p-value is, what information it tells us about an experimental result, and what it doesn't. After we define what a p-value is, we'll show how it's calculated in the context of a simple experiment of flipping a coin. The content of this video will be helpful for understanding results in the scientific literature and may also be useful if you decide to watch the videos in the Discoveries in Physics playlist. Okay, so let's start by describing what a p-value is. We'll imagine that you're conducting some experiment to measure a certain quantity that we'll call Q. You're measuring this quantity in order to distinguish between two hypotheses, called the null hypothesis and the alternative hypothesis. Under the null hypothesis, Q takes on the value Q0, and under the alternative hypothesis, it has the value QA. Typically, the null hypothesis is the prediction of known, understood scientific principles, while the alternative hypothesis is usually the prediction of some new and interesting, not well-tested idea. Let's look at a couple of examples to make this clearer. For example, let's say that it is well known that a person picked out of the population at random has a probability R0 of having a particular disease. You want to know if carrying a certain gene increases the probability of having this disease. You hypothesize that the rate of the disease among carriers of the gene is RA, which is some number greater than R0. So you find 100 people who carry this gene and you want to test them for this disease. Under your null hypothesis, the rate of the disease is the same as in the general population, and you expect, on average, 100 times R0 people out of 100 carrying the gene to have the disease. Under your alternative hypothesis, you expect, on average, 100 times RA people out of 100 carrying the gene to have the disease. Okay, let's look at another example. You're measuring the lifetime of a certain particle. In the standard model of particle physics, the lifetime of this particle is predicted to be τ0. However, you're interested in a speculative new idea which predicts, among other things, a different value for the particle lifetime, which we'll call τA. Here, the lifetime being τ0 is your null hypothesis, and the lifetime being τA is your alternative hypothesis. Now that we know what the null and alternative hypotheses are, we can define a p-value. Let's say you do your experiment and measure the quantity Q. Q0 is the prediction of the null hypothesis, and QA is the prediction of the alternative hypothesis. Let's call the result of your measurement Q measured. Now, to get the p-value, we do a thought experiment. First, we imagine that the null hypothesis is correct. Then, under the assumption that the null hypothesis is correct, we ask what would happen if you repeated your measurement many, many times. Due to measurement uncertainties, you would not obtain the value Q0 each time. Instead, your results will be distributed around Q0 in accord with your measurement errors. Now, we ask, what fraction of those imaginary experiments would give results as extreme or more extreme than the result that you actually got, Q measured? Or, equivalently, if we chose one of these imaginary results at random, what's the probability it would be as extreme or more extreme than the actual measured result, Q measured? And roughly speaking, by extreme, we mean farther away from Q0, but we'll clarify this in a bit. Note that the p-value is only a statement about how unusual your measured result Q measured is, assuming the null hypothesis is correct. If the p-value is very small, so much less than 1, that means there was a very small probability, under the null hypothesis, of getting a result as extreme as the one you obtained. Now, the p-value does not give you the probability that the null hypothesis, or for that matter, the alternative hypothesis, is true. It also does not tell you if your measured result is compatible with the alternative hypothesis. It only tells you, assuming the null hypothesis is true, how weird your result is. If the p-value is very small, you may conclude that your result, Q measured, is not compatible with the null hypothesis. In other words, you may conclude that the null hypothesis is false. Even in this case, it does not tell you that your alternative hypothesis is true. Instead, the truth may be a third hypothesis that you haven't thought of. Note that the alternative hypothesis is almost irrelevant in calculating the p-value. The p-value is a statement about the compatibility of the observed result with the null hypothesis. However, there is one way in which the alternative hypothesis is relevant. When we ask how extreme the observed value Q measured is, we often mean how far away is Q measured from Q0 in the direction toward QA. Okay, let's do an example. This example will involve flipping a coin. Let's say that a normal coin, when flipped, has a 50% chance of coming up heads and a 50% chance of coming up tails. But there is a company that makes novelty coins which come up heads 95% of the time. They're visually indistinguishable from normal coins. You decide to test if a coin you have is a normal coin or one of these novelty coins. Your null hypothesis will be that the coin is totally conventional and comes up heads and tails each 50% of the time. Your alternative hypothesis will be that you have one of the novelty coins that comes up heads 95% of the time. You decide you will flip the coin 10 times and see how many times it comes up heads. you decide to take the number of flips that come up heads as a measure of how extreme the result is. The more flips that come up heads, the more extreme the result is. Okay, you flip it 10 times, and it comes up heads 9 of those times. Let's get the p-value of this result. Okay, so the p-value is the probability, assuming the null hypothesis, that you would obtain a result as extreme or more extreme than the one you actually observed in your experiment. So here, the p-value is the probability, assuming the null hypothesis, of at least as many flips out of 10 coming up heads as occurred in your actual experiment. So it is the probability under the null hypothesis of obtaining either 9 or 10 heads out of the 10 flips. So let's calculate the probability of obtaining either 9 or 10 heads out of 10 flips under the null hypothesis. This calculation will hopefully be self-contained, but if you'd like more details on calculations like this one, you can check out the videos in the binomial statistics playlist. Okay, first, let's get the probability under the null hypothesis of all 10 flips coming up heads. Assuming the null hypothesis, the probability of having a given flip come up heads is 50%, or 1/2. The flips are independent, so the probability of having all 10 come up heads is 1/2 to the 10th power, which is equal to 1 over 1024. Okay, now let's get the probability, assuming the null hypothesis, of 9 of the 10 flips coming up heads. First, let's look at the probability of the first 9 flips coming up heads and the last 1 flip coming up tails. The probability of a single flip coming up heads is 1/2, so the probability of the first 9 coming up heads is 1/2 raised to the 9th power. The probability of the last flip coming up tails is also 1/2, so the probability of the first 9 coming up heads and the last coming up tails is 1/2 to the 9th power times 1/2, which is equal to 1/2 to the 10th power, which is also equal to 1 over 1024. Okay, so the probability, assuming the null hypothesis, of the first 9 coming up heads and the last 1 coming up tails is 1 over 1024. But we want the probability of any 9 coming up heads and any 1 coming up tails. There are 10 ways that this can happen. So the first flip can be the 1 flip that comes up tails, or the second flip can be the 1 flip that comes up tails, or the third or the fourth, etc. So the probability for any 9 flips to come up heads and any 1 to come up tails is 10 times the result we got a minute ago, 1 over 1024, and so that equals 10 over 1024. Okay, so assuming the null hypothesis, the probability for all 10 to come up heads was 1 over 1024, and the probability for 9 to come up heads and 1 to come up tails was 10 over 1024. So, the probability under the null hypothesis for either 9 or all 10 to come up heads is 10 over 1024 plus 1 over 1024, which equals 11 over 1024, which is about 0.011. This is the p-value of our result. Okay, so we've seen that the p-value is approximately 0.011. This means that if the null hypothesis is correct, there was only an approximately 1.1% chance of having as many of the flips come up heads as we actually observed. Now that we have that result, let's discuss a few points. First, the p-value only tells you, assuming the null hypothesis, how strange your observed result is. The p-value doesn't give you a probability that the null hypothesis or the alternative hypothesis is true. To illustrate this, note that we didn't mention in our example how likely it was before you flipped the coin for you to have a novelty coin at all. Let's imagine that these novelty coins are very rare, such that before you flipped the coin, the probability that you were carrying one was 1 in a million. So before you flip the coin, the null hypothesis is overwhelmingly likely to be true. After you've flipped the coin and had it come up heads 9 times out of 10, the null hypothesis is still overwhelmingly likely to be true. This is because while the probability of having at least 9 flips come up heads is only 1.1% under the null hypothesis, the initial probability of getting your hands on one of the novelty coins is much, much smaller. On the other hand, we can consider a scenario where the novelty coins are very common, such that any given coin before flipping is equally likely to be a conventional coin or a novelty coin. In this scenario, obtaining 9 heads out of 10 flips would make the alternative hypothesis, that you have a novelty coin, much more likely than the null hypothesis, that you have a conventional coin. If you'd like to know more about calculating the probabilities of the null and alternative hypotheses, you might want to know more about something called Bayes' theorem. You can find videos on Bayes' theorem in the Bayesian playlist. Okay, so the p-value does not tell you about the probabilities of the alternative or null hypotheses. It only tells you how weird your result is if the null hypothesis is true. Also, as we mentioned before, often the alternative hypothesis has an effect on how the p-value is defined. A p-value tells you how extreme or weird your result is under the null hypothesis, but different definitions of extreme are relevant for different circumstances. Let's take another look at our example. Here, we were interested in the alternative hypothesis that the novelty coins landed heads up 95% of the time. We asked, under the null hypothesis, what fraction of experiments would have had at least as many flips come up heads as were actually observed, which was 9. In other words, we asked what fraction of experiments would be at least as far away from the expectation of the null hypothesis, but in the direction of the alternative hypothesis. But we could imagine another scenario where the novelty coins had instead been made to come up heads 5% of the time and tails 95% of the time. Then it would be more appropriate to ask, under the null hypothesis, what fraction of experiments would have no more flips come up heads than were actually observed? And we could imagine yet another scenario. Let's imagine that the novelty coins came in both types, those which come up heads 95% of the time and those which come up tails 95% of the time. Here, the null hypothesis is still that we have a conventional coin that comes up heads and tails each 50% of the time. But now the alternative hypothesis is that you have either type of novelty coin. In this scenario, a more reasonable way to calculate the p-value would be to ask what fraction of experiments, under the null hypothesis, have a value of the absolute value of the number of flips that come up heads minus the number of flips that come up tails, at least as extreme or more extreme than that seen in the actual experiment. So if you flipped a coin 10 times and it came up heads 9 times out of those 10, you would ask what fraction of experiments under the null hypothesis would have had at least 9 flips come up heads or at least 9 flips come up tails. Okay, so let's summarize. Here we've looked at a tool called a p-value and given a demonstration of how it can be calculated for the example of flipping a possibly weighted coin. A p-value is a statement about how weird an experimental result is interpreted within the null hypothesis. It doesn't tell us the probability of the null hypothesis being true, however. And the p-value doesn't tell you if the experimental result is compatible with the alternative hypothesis or the probability of the alternative hypothesis being true. Strictly speaking, you don't need an alternative hypothesis to compute a p-value. But sometimes the alternative hypothesis is used for defining how the p-value will be calculated. In other words, which values are considered more extreme. So it can indirectly affect the p-value.